lecture 28, we're going to begin looking at polar coordinates, which is an alternative coordinate system to what we've traditionally used in previous math courses as the rectangular coordinate system or the Cartesian coordinate system. And we're going to learn how to plot points in this new coordinate system using polar coordinates, be able to convert between our two coordinate systems, polar coordinates to rectangular coordinates and vice versa, from rectangular to polar. And also then look at equations and what their graphs would look like. In fact, we're going to spend even more time looking at their graphs in lecture 29. So just as a review, let's recall the rectangular coordinate system, which the rectangular coordinate system is the system in which we take two real number lines and we assign to every point in the plane two coordinates based on a projection of that point down, straight down to what we call the x-axis and straight over to what we call the y-axis. And so this value on the x-axis we call x, or the first coordinate of the point, and this value where it hits the y-axis is called y. So if it hit 2 and 3, that would be 2, 3. But that's how we assign a location via coordinates as an ordered pair in the rectangular coordinate system. But let's consider an alternative method that takes advantage of some information we've covered in this class. Alright, so we're going to consider a point, and we're going to call, in this polar coordinates, we're going to call a point a pole, although I may still often refer to it as a point, but that's what we mean in polar coordinates by a pole. We're going to draw a ray extending from the origin through the pole. So a coordinate system called the polar coordinate system really only needs a positive x-axis. We're going to call that the origin right here. And this would be like the positive x-axis, at least in the way that it overlaps the rectangular coordinate system. And if you've got some point out here in the plane, instead of dropping straight down and going straight over, we're going to do is we're going to draw a ray through that point, extending through that pole. Okay, and we're going to label two values. R and theta are going to be called the polar coordinates of that point, instead of using x and y. Now, what are r and theta? R is the distance from the origin, called that because it's like a radius, and then theta is the angle made by the ray and the positive x-axis, which we will now call the polar axis. So let's consider plotting some polar coordinates, or points that are in polar coordinates. It's the best approach to generally find the angle first. So remembering that polar coordinates are given in terms of r, theta. We are told that these are polar coordinates, so we know that in this example, theta is pi over 4. So pi over 4 is exactly halfway between 0 and 90. It's a 45-degree angle. And then my r is 2, so if I go out 2 in that direction, that is in the direction of pi over 4, 1 unit, 2 unit, positive means go forward in that direction, along that ray. So that is the point A right there. Point B would be along the same direction. If this is pi over 4, then negative 2 would mean to go the exact opposite direction. That is, it's still in the direction of pi over 4, but now negative. A negative 2 would be 1, 2, right there for point B. If I were to plot 3, 0, again remembering the 0 is the theta, that means I'm in the direction of the positive x-axis. That's 0 direction. And 3 units, 1, 2, 3 is right there. That's point C, because I'm going away from the origin, a distance of 3. And then last of all, if 5 pi over 3 is theta, each of these lines is actually pi over 6, so there's pi over 3 would be almost all the way to 2 pi, because it's almost to 6 pi over 3. So actually it's right here, I believe, right? 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3 is right here. And a distance of 4 from the origin in that direction, 1, 2, 3, 4 would be right there. There's my point D. That's how we plot points using polar coordinates. There is one interesting point to be made about the polar coordinate system, and that's that unlike the rectangular coordinate system, a point with polar coordinates can actually have multiple representations. And to illustrate that, let me start by plotting the point 5, comma 2 pi over 3. Now 2 pi over 3 we know is right here. This is 2 pi over 3, the angle. And going 5 out in that direction, 1, 2, 3, 4, 5, puts me right there on this point. Okay, now the reason why you can have multiple representations is we have one name or one measure for this angle, but alternatively we can get to that same angle by coming from this side all the way over to here, right? That would be, if I go backwards, that's negative pi over 3, 2 pi over 3, 3 pi over 3. This is the same thing as negative 4 pi over 3. So I could rewrite that point as 5 comma negative 4 pi over 3, and it would be the same point. And that's what this first answer would be, because this asks for find the polar coordinates such that r is positive, meaning I'm going out in that direction, but theta is between negative 2 pi and 0. That is, it's a negative angle, but it's within one rotation, and that's what negative 4 pi over 3 would be. So this answer would be 5 comma negative 4 pi over 3. On the next one it says let's do this in the positive direction for the angle, but find a point that's the same point, that is, find the coordinates that's the same point but where r is negative. Now how could that possibly happen? Well, let me switch colors again. Let's go to a green here. Notice that if I were to go in this direction right here, right? If I went a positive 5 down there, I would actually end up at this point, which is not where we want. But if I chose this direction that I have written in green, but then picked a negative 5, that would require me to go backwards 1, 2, 3, 4, 5, and end up at that same point. So whatever this angle is right here, if I were to put a negative 5 on it, that would get me to the same point. So going around this way to get to the green, that is 5 pi over 3. Now, of course, the last and most obvious thing you could have done is you could do multiple rotations. So, for example, instead of going around once, let me just so you can see this, let me erase what I've all drawn on this graph here. Instead of going around once to this, or going once to that point, what if I went around a completely separate time? Right, that makes 2 pi over 3 the same thing as 2 pi over 3 plus 2 pi, or 2 pi over 3 plus 6 pi over 3, or an 8 pi over 3. So I can still go a positive 5 in that direction, but now choose my direction to be 8 pi over 3. So positive 5 comma 8 pi over 3 is between 2 pi and 4 pi. That means it's more than one rotation, but less than 2 rotations. So we can convert any point to multiple representations if we have need to do so. We know the rectangular coordinate system well because that's what we've covered in most math classes to this point. So one of the things that we need to be able to do well is to understand the relationship between this new coordinate system, which will have some pretty interesting applications as we move forward. But, pardon me, we will want to be able to convert between the two. So if I gave you a point in rectangular coordinates, can we convert it to polar? And if I gave you a point that is in polar coordinates, can you convert it to rectangular? Now we're going to start with the easier of those two. Actually, neither is too bad, but converting from polar coordinates to rectangular coordinates is actually a very simple application of a couple of formulas. Formulas that we'll be familiar with, having seen them before. So here's a little theorem. It says if we're given a point, r theta, in polar coordinates, the rectangular coordinates for that same point r x comma y, where x can be found as r cosine theta and y can be found as r sine theta. Now, where does that come from? Well, if you think about where that point is, and I'm just going to draw an arbitrary point here on the polar coordinate system. Remember, with the polar coordinate system, all you got to start with is the origin and the polar axis, which is the positive x-axis. You draw a ray out through that point, and you know this distance here is called r, and this angle here is called theta. Now let's superimpose on top of this a rectangular coordinate system. So those two lines are coincident. They're the same thing. And so I'm going to go left and right, still making that the origin, but I'm going to go up and down as well. I'm going to call this the x-axis and this the y-axis. So the question now is, if I were to drop this point straight down, where would it hit the x-axis? And if I were to drop this point straight over, where would it hit the y-axis? All right, we want to know what the x and y coordinates of that point happen to be. Well, the easiest way to think of it is in terms of our definitions of trig functions, our theorem that relates a point on a ray with an angle theta. We know that sine of that theta is the y-coordinate over the radius. We also know that cosine of that theta is the x-coordinate over the radius. And all you got to do to figure out my two formulas that I wrote down right here is multiply r to the other side. On these guys. Okay, and the result is y is equal to r sine theta and x is equal to r cosine theta. Voila, that is proved. Right? So to convert this, we just recognize that my 6 is my r, since it's given in polar coordinates, and my pi over 6 is my theta. So x would be r cosine theta, which is 6 cosine of pi over 6, and y would be r sine theta, which is 6 sine of pi over 6. And of course we know our sines and cosines for pi over 6. Cosine is square root of 3 over 2, so we got 6 times square root of 3 over 2, and sine of pi over 6 is 1/2, which gives me 3 square roots of 3 and 3. So my coordinates in the rectangular coordinate system would be 3 square roots of 3, comma 3. Let's go back the other way now. Let's say we're given rectangular coordinates and we want to find their polar coordinates. So given x and y, we need to find r and theta. Part of that question is relatively easy, that is finding r. We've done that before in some of our previous problems because r is that distance from the origin. So step 1, plot the point x, y. We're going to need to know the distance from the origin and then the theta of the angle whose ray extends through our point. It's going to be helpful first to know what quadrant we're in. In fact, we're going to need that to find our theta. Step 2 is the easy one. Again, it's finding r. We're going to use x squared plus y squared equals r squared. So consider that equation. You know x and you know y, so all you have to do to find r is to solve that equation. Now, finding theta gets, there's just one little trick to it. And the problem with finding theta is that we're going to use a trig function to do it. But if we know the value of a trig function, like, for example, sine of theta or tangent of theta is equal to some number, finding the angle means we're going to have to use inverse trig functions. And there's a limitation on inverse trig functions, and that's where the output is. The range of a inverse trig function gives us a problem, right? Because we only get numbers out of it on half of the plane, and it's very possible that our theta is somewhere else. So I'm going to walk you through the process that I use to find the theta every time. First thing you do is plot the point and determine what quadrant it's in. Now, obviously, if the point is on an axis, you're done. It's a piece of cake because you know what the angle for each of the axes would be. But what if it's not on the axis? What do we do then? You basically have 4 cases. You're either in quadrant 1, quadrant 2, quadrant 3, or quadrant 4. To figure out this angle that I have called theta sub r, which is I'm going to call it my reference angle. All you have to know is the fact that tangent of that theta is always going to be y over x. And in fact, it's the absolute value of y over x. Is why we're always finding an acute or a less than right or less than 90 degree angle. If you take the tangent inverse of y over x, remember you're given x comma y. So if you take y, tangent of theta, this is the easiest example here, tangent of theta sub r is y over x. And if you move to another quadrant, you may have the positive negative value of y or x may be negative or positive. So in order to always find just what's called the acute version of that angle, we're going to use the absolute value of that. And that's this equation right here is true for all four of these cases. But again, it's only finding that little angle right there. This I can plug into my calculator and will always give me an angle between 0 and pi over 2. So to get the actual angle, then we just got to realize what does theta look like if we know theta sub r. So in the first quadrant right here, theta and theta sub r are the same thing. They're still just that angle right there. But theta sub r is this guy over here in quadrant 2. So how do I find theta? Well, how do I find this angle that I'm looking for? And that angle theta right there is all of pi minus the reference angle. So I get this formula, pi minus theta sub r. Now, if I wanted to find the theta, which is all the way from the positive axis down to the third quadrant, and I've found this little angle inside here, all I got to do in that quadrant is take pi plus my theta sub r. And then if I want to find this theta here, and I'm given this, notice that's all of 2 pi minus that little angle, so 2 pi minus theta sub r. So I've just got to remember, if I'm in quadrant 1, whatever I get from this formula right here is my theta. If I'm in quadrant 2, I'm going to take pi minus that. If I'm in quadrant 3, I'm going to take pi plus that. And if I'm in quadrant 4, I'm going to take 2 pi minus that. 3 shouldn't be there, sorry. All right, so let's do that. Again, finding r is simple. Finding theta, you just got to apply this formula for tangent inverse of the absolute value of y over x. That gives you your reference angle, and then for whatever quadrant you're in, you can find your actual theta from your reference angle. I'm going to start us off with an easy one here. If you go to -3, 0, and remember these are rectangular coordinates, so you know you're going -3, 0. So there's your point. So now you draw your ray that goes through that point, starts in the origin and goes through that point. First thing you need to know is what's r. Okay, r, distance from origin, is clearly 3. I don't even have to work out the problem. I could do x squared plus y squared equals r squared, which means -3 squared plus 0 squared is r squared. So 9 plus 0 is r squared. 9 equals r squared, so r is 3. Right? Or I could just have counted. In this particular case, that's actually simple. I get 3. Now to get theta, because it's on one of my axes, I know theta is pi. I don't even have to do any work to get there. So when it lands on an axis, life is easy. So your polar coordinates are 3 comma pi, and you're done. All right, so let's kick it up a notch, shall we? Find the polar coordinates of a point whose rectangular coordinates are square root of 3 comma 1. So that's my x and that's my y. So let's start by plotting where this is. First of all, both of these are positive. Square root of 3 is about 1.7, so it's between 1 and 2, right about here. And y is up 1, so we're right here. So I'm going to draw my ray through that point. I'm trying to find this theta and this r. So I know I'm in quadrant 1. That's going to be useful in my third step from the instructions above. We've got the thing plotted, so step 2 is to find r. So we'll use x squared plus y squared equals r squared. So square root of 3 squared plus 1 squared equals r squared. So that's 3 plus 1 equals r squared. 4 is equal to r squared. R then is equal to 2. Now, of course, just keep in mind, in this case, we have talked about r having a negative value. We just go in the opposite direction. But since we're finding this theta here and not the theta that's in the opposite direction, we know we're talking about r being positive because we're moving along that direction. So we're going to let r be the positive value that whenever we take the square root of 4, we get that positive number. Okay, what about theta? Okay, so we start by taking theta sub r to be the tangent inverse of y over x, 1 over the square root of 3, or the tangent inverse, and it's it's the absolute value, so we're dropping any negatives if we had them, but we don't. So it's actually tangent inverse of square root of 3 over 3, which we actually know what angle has a tangent inverse of positive square root of 3 over 3. Pi over 6, so theta sub r. Now, since we're in quadrant 1, that means theta and theta sub r are the same thing, so I've got my theta is pi over 6. So my polar coordinates would be 2, comma, pi over 6. Boom, just like that. Okay, so find it in the quadrant, find the reference angle, and then for whatever quadrant you're in, identify what theta is relative to that reference angle. Now, since we can transform coordinates, that is individual points, we can also transform equations. Equations represent a whole set of points that satisfy that equation. We can transform from one way to the other by using any of our formulas that we have utilized in the conversion for individual points. So if I have a formula or an equation in terms of x and y, I can simply replace all the x's with r cosine theta and all the y's with r sine theta. So it's easy to go from rectangular to polar when you're converting equations. Unlike when you're converting points, it was easier to go from polar because you knew r and theta. You could just plug them into the formula, get x and y. If we want to go in an equation, you want to replace all of your variables with the other variables. So if you have x's and y's in the equation, you want to change them to r's and thetas. If you have r's and thetas, you want to change them to x's and y's. So it's a little bit more challenging to do a conversion that involves r's and thetas because you have to get it in terms of r squared. You also need to see things like tangent of theta show up in there to be able to do the conversion. So for example, if I had r is equal to 6 cosine of theta. Now we'll talk about in the next lecture what a graph of a polar equation turns out to look like, because it actually gets some interesting shapes, far different from what we would normally have seen with a rectangular coordinate system for an equation. But before we look at what the graph looks like, let's just simply write this thing down in terms of its rectangular form. So the trick here is I don't have any formulas that directly convert r to an x and a y or the theta to an x and a y. All I have is r squared and tangent of theta instead of cosine of theta. So what we're going to do is be creative here. And this little trick you're going to use on a few of your homework exercises as well. Let's manipulate the equation so that there is an r squared in there. What might we do to get an r squared in there? The first guess might be to square both sides, but the problem with squaring both sides is you still end up with a cosine squared over on the right hand side, which doesn't help us. But another thing we could do to get an r squared is to multiply both sides by r. And the beauty of that is you do end up with an r squared on the left, which I have an equation for. But you also end up with a 6r cosine theta on the right, and I also have an equation that converts r cosine theta into x. In other words, this now looks like x squared plus y squared is equal to 6x. I have now converted that polar equation into a rectangular equation. right? Because r squared is x squared plus y squared. I just replaced it on the left-hand side, and then r cosine theta is just x, which I replaced on the right-hand side. Once you get rid of all the r's and thetas, you're done. You've converted from polar to rectangular. Again, going the other way is the simple case, although you want to do a little bit of algebraic simplification when you're done. Just remember here that x is r cosine theta and y is r sine theta. So 4xy equals 9 becomes 4 times r cosine theta times r sine theta. I'm just substituting in, equals 9. So 4r squared cosine theta sine theta equals 9, which is good enough for me. Although you could simplify that further using things like trig identities, but at the point that you've got rid of all the x's and y's, then you are basically done.